When we repeatedly draw samples of size n from a population and compute the average of each sample, those averages themselves form a new random variable called the sample mean, x bar. The collection of all possible x bar values together with their probabilities is called the sampling distribution of the sample mean. If the original population follows a normal distribution with mean mu and variance sigma squared, written as x is distributed as normal of mu and sigma squared, a special and very convenient fact holds. The sample mean is also normally distributed, no matter what the sample size n is. Formally, x bar is distributed as normal of mu and sigma squared over. The mean of the sampling distribution equals the population mean. E of x bar equals mu, which tells us the sample mean is an unbiased estimator of mu. The variance of x bar shrinks by a factor of n, reflecting the idea that averaging smooths out random fluctuations. Real-world analogy: imagine measuring the daily sales of a coffee shop. Each day's sales amount is a random draw from a normal-like pattern. If you look at the average sales over a week, the week average will also follow a bell-shaped curve, centered on the true average daily sales, but with a tighter spread because you have combined 7 days of information. The standard error, abbreviated SE, measures how much the sample mean x bar is expected to vary from sample to sample. It is simply the standard deviation of the sampling distribution of x bar. Starting from the exact variance result for a normal population, variance of x bar equals sigma squared divided by n. The SE is the square root of that variance. SE of x bar equals the square root of variance of x bar equals sigma over the square root of n. Derivation steps. Each observation x sub I has variance sigma squared, and the observations are independent. The variance of a sum of independent variables is the sum of the variances. Variance of the sum from I equals 1 to n of xi equals n sigma squared. The sample mean is the sum divided by n, so its variance is variance of x bar equals variance of 1 over n times the sum of xi equals 1 over n squared times n sigma squared equals sigma squared over n. Take the square root to obtain the SE. Interpretation: SE tells you the typical distance between the sample mean you compute and the true population mean. A larger sample big N makes the denominator bigger, so the SE gets smaller, your estimate becomes more precise. In business, if a market research firm surveys 400 customers instead of 40, the SE of the average satisfaction score drops by a factor of the square root of 10, giving a tighter confidence band around the reported average. Explanation: the central limit theorem, abbreviated CLT, is the workhorse of statistical inference. It says that under fairly mild conditions, the distribution of the sample mean, or any sum of independent, identically distributed random variables, becomes approximately normal as the sample size grows, even if the original data are far from normal. Formal statement: let x sub 1, x sub 2, x sub n be independent and identically distributed random variables with finite mean mu and finite non-zero variance sigma squared. Define the standardized sum z sub n equals the sum from I equals 1 to n of xi minus n mu divided by sigma times square root n, which is also equal to x bar sub n minus mu divided by sigma over square root n. Then as n goes to infinity, the distribution of z sub n converges to the standard normal distribution n of 0, 1. Required conditions. Independence: the draws must not influence each other, such as simple random sampling or independent experiments. Identically distributed: each draw follows the same population distribution or at least shares the same mean and variance. Finite variance: if the variance is infinite, for example a Cauchy distribution, the central limit theorem does not hold. Proof sketch: Lindeberg-Feller approach simplified. Start with the moment generating function, m sub x of t, equals the expected value of e to the tx. For the sum s sub n equals the sum of xi, the moment generating function is m sub s n of t equals m sub x of t raised to the n, because the observations are independent. Expand m sub x of t around t equals 0 using a Taylor series. M sub x of t equals 1 plus mu times t plus sigma squared times t squared divided by 2 plus little o of t squared. Plug into m sub x of t divided by sigma square root n raised to the n and let n grow. Higher order terms vanish, leaving e to the t squared over 2, the moment-generating function of n of 0, 1. By the uniqueness of moment-generating functions, the standardized sum converges in distribution to a normal distribution. In business language, the central limit theorem tells you that the average of many independent sales figures, defect counts, or customer ratings will look bell-shaped, letting you apply normal theory tools even when the raw data are skewed or discrete. A sample proportion p hat is the fraction of successes in a sample of size n. For example, if 30 out of 120 surveyed customers say they would buy a new product, p hat equals 30 divided by 120 equals 0.25. The exact sampling distribution of p hat is binomial scaled by 1 over n. P hat equals x divided by n, where x is distributed as binomial with parameters n and p. When n is large and the true proportion p is not too close to 0 or 1, the central limit theorem lets us replace the binomial shape with a normal curve. The key steps are: Step 1. Recognize that x is a sum of n independent Bernoulli trials. Each trial equals 1 for success, 0 for failure, with mean p and variance p times 1 minus p. Step 2. Apply the central limit theorem to the sum x. The standardized sum z equals x minus np divided by the square root of np times 1 minus p. Approaches a normal distribution with mean 0 and variance 1 as n grows. Step 3. Divide by n to get the proportion. Algebra gives the approximate normal distribution for p hat. P hat is approximately normal with mean p and variance p times 1 minus p divided by n. Rule of thumb: the approximation is generally safe when both np is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5. Business illustration: a retailer wants to know the proportion of shoppers who would respond to a new loyalty program. They sample 400 customers and find 120 say yes. Because np equals 400 times 0.3 equals 120 and n times 1 minus p equals 280 are both well above 5, they can treat p hat as normal with mean 0.3, and standard error the square root of 0.3 times 0.7 divided by 400 equals 0.0229. This normal approximation enables quick confidence interval and hypothesis test calculations. When you sample without replacement from a finite population of size n, each draw slightly changes the makeup of the remaining pool. This effect reduces the variability of the sample mean or proportion compared with the idealized case of infinite or effectively infinite populations, where draws are independent. The adjustment is called the finite population correction, FPC. For the sample mean, the exact variance is var x bar equals sigma squared over n times n minus n divided by n minus 1. The factor n minus n divided by n minus 1 is the FPC. It is always less than 1. So the variance and the standard error become smaller as the sampling fraction n over n grows. When to apply, use the FPC whenever the sample size is a non-trivial fraction of the population, commonly when n over n is greater than 0.05, more than 5%. If you are drawing only 20 observations out of a million customers, the correction is negligible and can be ignored. If you audit 80 out of 100 invoices, the correction matters a lot. Impact example: suppose a company has n equals 500 factories and wants to estimate the average annual output. They sample n equals 100 factories. Ignoring the FPC, the standard error would be sigma over square root of 100. With the FPC, the standard error becomes sigma over square root of 100 times the square root of 500 minus 100 divided by 500 minus 1 equals sigma over 10 times the square root of 400 divided by 499, approximately 0.894 sigma over 10. The standard error is about 10% smaller, giving tighter confidence bounds. The same correction works for proportions, replacing sigma squared with p times 1 minus p. Explanation: a confidence interval CI gives a range of plausible values for a population parameter, here the mean mu, based on a sample. The CLT supplies the normal approximation that underlies most large sample CIS. Case 1 known population standard deviation sigma : if sigma is truly known, rare in practice but useful for theory, the sampling distribution of x bar is exactly n of mu. Sigma over root n a 100 times left parenthesis 1 minus alpha right parenthesis percent confidence interval is x bar plus or minus z sub alpha over 2 sigma over root n, where z sub alpha over 2 is the critical value from the standard normal, for example 1.96 for 95%. Case 2 unknown sigma colon. Typically we estimate sigma with the sample standard deviation s for moderate to large n. The CLT still justifies using the normal quantile, yielding the approximate confidence interval x bar plus or minus z sub alpha over 2s over root n. If n is small, say n less than 30, and the population is normal, we replace the normal quantile with the student t quantile with n minus 1 degrees of freedom, giving the exact t interval. Interpretation colon. The interval says that if we repeated the sampling process over and over, about 1 minus alpha of those intervals would capture the true mean. In a business setting, a manager might report, based on a random sample of 200 customers, the average monthly spend is $125 with a 95% confidence interval of $119 to $131. The width of the interval reflects both sample size and variability. Larger n or smaller variation shrinks the interval, giving a more precise estimate. Finite population. Note colon. If sampling without replacement from a known finite population, replace sigma over root n with root of left parenthesis n minus n right parenthesis over left parenthesis n minus 1 right parenthesis times sigma over root n using the finite population correction. A large sample z-test for a proportion evaluates whether an observed sample proportion p hat differs significantly from a hypothesized population proportion p0. The test rests on the central limit theorem approximation that p hat is approximately normal. Test statistic z equals p hat minus p0 divided by the square root of p0 times 1 minus p0 over. The denominator is the standard error computed under the null hypothesis using p0 instead of p hat. Decision rule. Choose a significance level alpha, for example 0.05. Find the critical z values. For a two-sided test, reject the null hypothesis if the absolute value of z is greater than z sub alpha over 2. For a one-sided test, reject if z is greater than z sub alpha for a right tail, or if z is less than negative z sub alpha for a left tail. Assumptions. Simple random sample, independent draws. Sample size large enough that n times p0 is at least 5, and n times 1 minus p0 is at least 5. Business example. A bank claims that at most 8% of loan applicants default. In a random sample of 500 applicants, 48 default, giving p hat equals 48 divided by 500 equals 0.096. Test the null hypothesis that p equals 0.08 versus the alternative hypothesis that p is greater than 0.08. Compute z equals 0.096 minus 0.08, divided by the square root of 0.08 times 0.92 over 500 equals 0.016 divided by 0.0121, approximately 1.32. With alpha equal to 0.05, the critical value is z sub 0.05 equals 1.645. Because 1.32 is less than 1.645, we fail to reject. The data do not provide strong evidence that the default rate exceeds 8%. The z-test is quick, needs only the proportion and sample size, and is widely used for market share comparisons, conversion rate analyses, and quality control pass rate assessments. Population characteristics. Exponential probability density function, f of x equals lambda e to the minus lambda x greater than or equal to 0. Mean mu equals expected value of x equals 1 over lambda. Variance sigma squared equals 1 over lambda squared. Sample mean definition. For a random sample x sub 1 through x sub n, x bar equals 1 over n times the sum from I equals 1 to n of x sub I. Apply the central limit theorem. The xi are independent and identically distributed with finite mean and variance, so parentheses x bar minus mu divided by sigma over square root of n parentheses converges in distribution to normal of 0 mean and unit variance as n goes to infinity. Substituting mu and sigma, x bar is approximately normal with mean 1 over lambda and variance 1 over lambda squared n. Hence, the approximate sampling distribution of the sample mean is normal with mean 1 over lambda, and standard error 1 over lambda times the square root of n. Interpretation: even though the exponential distribution is heavily right-skewed, the average of a moderate number of observations behaves like a bell curve. The larger n, the tighter the spread. Suppose the time between customer arrivals at a help desk follows an exponential distribution with average 5 minutes. Hence, lambda equals 1/5 equals 0.2 per minute. A manager records the inter-arrival times for 36 customers. Using the central limit theorem, the sampling distribution of the average inter-arrival time is approximately x bar follows normal with mean 5 minutes and standard deviation 5 divided by square root of 36, which equals 0.833 minutes. If the observed sample mean is 5.4 minutes, the standardized z-score is z equals parentheses 5.4 minus 5 close parenthesis divided by 0.833, approximately 0.48. Well within the usual plus or minus 1.96 range, so the observed average is consistent with the assumed exponential model. Exam-style answer checklist. State population mean and variance of exponential. Show the central limit theorem expression and plug in mu and sigma. Write the resulting normal approximation. Mention that the approximation improves with larger n. Provide a concrete numeric illustration as above to demonstrate